So hello everyone, welcome back to the another lecture. So my name is Ashish and today we will see a flyback converter. Okay, so what things we are going to cover in this video is operation principle of the flyback converter. We will not go in much more detail like how this particular flyback converter is formed. Okay, but we will try to understand its operation principle. So how this particular things it work and all, why this dot convention are very important. All those things we will see. Then the design calculation. So people will talk about the flyback converter and its waveform, but people are not talked about the design calculation. So like how to design the value of the C, how to design the parameter of this transformer LM, which is a magnetizing inductance, which is very important in the flyback converters. How to design that, how to ensure that it is in CCM or DCM. So those things we will talk. And then the Matlab simulation part. So I have seen the videos are available on YouTube as well for the Matlab simulation for open loop, but I feel something is missing there or something you might not get from those videos. So that is why I personally studied this particular topic in detail and I have come up with this video. So we will simulate the open loop as well as closed loop simulation in this video for flyback converter. So overall we will see the complete things about the flyback converter in this particular video. So I hope so you will enjoy this video and you will learn something from me. So let's get started with this video. So for discussing all this thing, I have prepared one document for you. Okay, if you need it, I will share this particular document with you. So this is a complete document for flyback converter design and its analysis part. Okay, and Matlab simulation part we will see in the Simulink window. Okay, so let's get started with this. So flyback converter design. So all you know that how the flyback converter looks like. Okay, so we have a one DC source. Okay, we have our one transformer model, and inside the transformer model, this LM is shown and one switch is also there. Okay, and then this transformer secondary side we have one diode, one capacitor and our load connected. Okay, so flyback converter is kind of the step up as well as step down converter. Okay, so either I can boost my output voltage or I can buck my output voltage, and isolation is also there. So this particular isolation is very important when we go for some critical application. But if we use this some normal buck converter, boost converter or buck boost converter, there is no isolation as well. Okay, so that is why this converter topology is isolated type kind of topology which we can use. Okay, for buck as well as boost mode. Okay, now few more important thing about this is like why this particular, how this particular topology has been come up. Okay, so those part I am not going to cover, but what things you can see here apart from this. So what key observation you should have. So you have this particular switch. Okay, the switch has basically this particular is a drain terminal. If I take the MOSFET and this is my source terminal. Okay, so I have seen that sometimes people basically use this particular switch here. Okay, but that is the wrong thing. Okay, you should not do that particular mistake in future, because this source is always with respect to ground. Okay, so this source should be connected to the ground. If you connect the switch here, that time your drain is connected to the positive supply, but your source is connected to the transformer. Okay, so that should not be the case. It should always be connected with respect to ground in this particular topology. So that one mistake is there, so you should keep this thing in your mind. Apart from this is basically this polarity. So polarity is also very important thing. You can see the polarity is here. Polarity meaning, so if this is positive, then this should also be a positive. Okay, now what will happen if this particular thing is not there? Okay, so I will just demonstrate you in another slide. So here we are. So you can see that what I have done, I have drawn one flyback converter. I have keep the polarity same. Now this particular switch which is there, that control is in our hand. Okay, so whenever I give the gate signal, it should be on. Okay, and whenever I remove the gate signal, it should be off. Now let us say I have applied the gate pulse here. Okay, my switch is on, so it is short circuited, and I have polarity of the dot is here as well as here. Okay, now if I will apply the KVL, so what will I get? So minus of Vs plus basically this V1, that plus V1 is equal to the 0. Okay, so what I am supposed to get in first particular half, when switch is on, that time my inductor is V1 is nothing but the VLM. Okay, so my inductor is charging. On the same time, what is happening? Basically this is positive. Now output voltage initially 0, so some voltage which is coming V1, this is going to be transferred to the V2. Now this particular diode is also conducting. Okay, and if this is conducting, this is short. Okay, so I am getting output should be equal to the V2 in the first half only. Now when I am saying that when my gate pulse is removed and when switch is off, okay, so that time you can see that when switch is off, so this polarity be changed and this is also going to be changed. Now the energy which is stored in the inductor, that is not going to be transferred because my diode will also going to be off in second case. Okay, so that is why we can't keep the polarity in such a way. Okay, we have to keep the polarity in this way only. So one at the top, another at the bottom. So this diode should be connected to the opposite polarity only. So this is the fundamental difference you should keep in your mind. If somebody asks you like what will happen if basically we will keep the dot convention like this, you can try and you can simulate. You may get some result, but that is not right. Okay, because your inductor which is charged LM, that there is no path to discharge it. It can just basically circulate here itself. Okay, so that is not the case. Now second thing which you should know about basically flyback converter is that, okay, so I have this particular flyback converter. So we will generally use basically this parameter Lm, that is the magnetizing inductance of the transformer. I hope so you know about the transformer basics. So that is inside basically my transformer itself. Okay, but generally for basically understanding purpose we will draw it outside. Okay, Lm, but only Lm is there? No, there Rm as well. Okay, you can see this particular graph. Okay, so Rm and Lm in parallel you can see, okay, inside there, which is there in the transformer. Okay, but generally we will keep this Rm as infinite and we will open this and I will just show it by Lm. Okay, but Lm only not the thing which is available in the transformer. Okay, now what we will going to do, we will try to understand the complete operating principle. Okay, so far so now I guess you have learned about what is the circuit, why the dot polarity are keep like this and all. Okay, now we will jump to our basically document and we will try to understand its operating principle one by one. So here we are again. So the operating principle is like I have already told you that the flyback converter is an isolated DC-DC converter topology that stores the energy in the transformer magnetizing inductance. This Lm here, it will store the magnetic inductance when switch is on and transfer the energy to the output when switch is off. Okay, so the transfer of the energy is very important. That is why this dot polarity is like this. Okay, now next some assumption I am taking that let my Vs is the input voltage, V0 is the output voltage, ILM is the magnetizing current which is flowing through this particular branch, Is is my source current. Okay, this is the D1, IC is the capacitor current, this is my V0, and let us assume that I0 is my output current. Okay, so I am keeping some I0 value which is my output current. Okay, and this is a Q is my switch. Now we will start analyzing this circuit one by one. Okay, now switch is on, first mode I am talking about. So when switch is on, what is going to be happen? Okay, when switch is on, my current will flow through this particular branch. Okay, so switch is on, current will flow through this particular branch and my diode is off. Okay, so what you are seeing, minus of Vs plus this particular V1, and V1 is my VLM. Okay, I called this, the voltage across this LM is VLM. Okay, and current flowing through this is ILM. So minus of Vs plus this particular V1 is equal to the equal to 0. So I have write it down here, Vs minus of V1 plus Vs equal to 0. So I can write it down, V1 equal to the Vs. Now what is this particular V1? V1 is basically voltage across the inductance. So I can write it down it as L dIL by dt. Okay, L dIL by dt. Okay, so this expression you know, L dIL by dt. And next to that what I have done is that just I transferred this L here. So what I got initially when switch is on, dILM by dt is equal to the Vs by Lm. Okay, so this is the first expression I got. Now we will move to the mode 2. So in a mode 2, basically what is going to happen, my switch will be off. Now you can see here, now in mode 2 switch is off. So what will happen, basically this is now basically polarity may change and my diode will start conducting, and whatever the basically energy stored in the LM, that is transferred to the now secondary side because my diode is now conducting. So what expression I should get here, minus of V2, this is plus, so I will write plus V2 plus V0 equal to 0. Okay, so this is how I can write it down. So what expression I guess, plus V2 plus V0 equal to 0. So I would say V2 equal to minus of V0. Okay, so this is I am getting. Now we have some transformers, some basic parts. So we know that V1 by V2 equal to N1 by N2. Okay, but what is the case here is that my V2 is equal to minus of V0. You can see during the off time. So what I have written down here is that V1 equal to minus of N1 by N2 into V0. Okay, So now V1, again you know what is V1. V1 is L dilm by dt. So I can write it down basically dilm by dt is equal to V1 by Lm. That is I have just substituting the value of the V1. So what I am getting is that minus N1 by N2 into V0 by Lm. So this is the another expression which I got during the turn of time. So I hope so. How to write it down, this basically a KBL, you know, I hope so. And how to operate the mode when switch is on, how to write down when switch is off, how to write it down. Okay, now the third important thing is we have to derive the expression for output voltage. So what I am going to use my volt second balance. Okay, so this is the very fundamental thing. So what happened in volt second balance, my output voltage during the on time I will represent it as a dt, okay, and off time I will represent it as my 1 minus dt. Okay, so what will happen in volt second balance is that at steady state the average voltage across the magnetic inductance over a complete switching cycle is 0. So this is, should be the case. Okay, my basically VL value should be equal to 0. Okay, so it is something like this will happen, and this particular part and this particular part should be equal in area, and that's why they are cancelled out here, and my average on VL across one particular switching cycle should be equal to 0. Now I will apply the volt second balance. What will I write it down? So initially I know that when switch is on, my basically V1 equal to the Vs. My output voltage is what? My output voltage is 0. So I will write it down. I will apply. I am applying for VL. So what is my VL in first case? That is Vs. Okay. So I write it down Vs into the dt. Okay. This particular part. Now second part is what is my basically V1 second more time. So my V1 is basically you can see here is that N1 by N2 into V0, okay, into the Lm. Something is there. Okay, you can see here. Okay, so what is my V1? N1 by N2 into V0. So that thing I have written down and multiplied by 1 minus dt, because this is the off duration. Okay, and its overall sum should be equal to the 0. Now if I will try to solve this, I am getting the value of the V0, and this is a well-known standard expression for the basically output voltage of the flyback converter, that is N2 by N1 into D divided by 1 minus D into the Vs. Okay, so here I have considered the polarity of the output as plus and minus. That's why I am getting the output in the plus. Okay, otherwise it should come into the minus as well if I will change the output voltage polarity. Okay, so this thing you should keep in your mind. So sometime you may find out V not equal to minus N2 by N1 into D upon 1 minus D into the Vs, because they consider the output voltage polarity like above is a plus, below is a minus. Okay, so that is totally depend on how you take the conventions. Okay, but fundamentally you should know V not equal to N2 by N1 into D upon 1 minus D into the Vs. So this is the well-known formula we know. So far, so now we understood a few more things, right? About how to apply the volt second balance and all. Now we will move forward and we will see few more things. Okay. So this is the expression you got, and this is a well-known expression. Okay. So don't confuse with this. So V naught is N2 by N1 D upon 1 minus D into Vs. Now we will talk about the switching analysis part. Okay. So this particular thing is very important, because now we will go to design the parameters. Okay. So how to design the parameters and all those things we are going to study. Now the switching analysis. Now the magnetizing inductance Lm when switch is on, what is happening? Okay, so something is written down that delta Lm is equal to Vs into dt divided by delta Lm. So how this particular thing is came? Okay, so let us take any case like when switch is on or switch is off. You can take any. Okay, now when switch is on, I will consider, so what will happen that my inductor current, that magnetizing inductance current will linearly increase from IL minimum to IL maximum. Okay, so you know that this is particular nature of the inductor current. Okay, right. So it is basically, if I'll consider the on duration, it will be increased from some minimum value to some particular maximum value. Now during this particular time we have seen that, okay, here what is my expression, that V1 equal to Vs. So from that, so dilm by dt equal to Vs by Lm I am getting. Okay, now how we have came to this particular expression I will show you. So I have just written down the things for you here. Okay, so I have told you that when switch is on, my V1 equal to Vs. And what is V1? V1 is my VLM. Okay, VLM equal to Vs. What is VLM? L dilm by dt equal to Vs. So I can write it down, dilm by dt equal to Vs by L. Now I am integrating both the side. Okay, and now this dt term I have transferred here. So what I am getting is that integration dilm. So its value should be gone from minimum IL minimum to IL maximum, and this is the on duration. So dt should be go from 0 to dt. Okay, this is a t on. Now if I integrate this, I am getting IL max minus IL min equal to delta ILM, and this is delta ILM I have calculated there, and what it is getting is that Vs by L into the dt. Okay, and if I wanted to calculate this L, which is basically my Lm, then I can just shift this particular term in that particular side and this delta Ilm in the denominator, and I'm getting the things right. So just I have written down for you so that you don't have any confusion like how this particular things is derived. Okay, now we will go to the our basically document. So I hope so you understood that how we have calculated this Lm value. Okay, so this is the value of the Lm which we should consider while designing. Okay, so we will see that what should be the minimum value which we have to take. Okay, but this is the standard formula which we have derived for basically calculating the value of the Lm. So now when you design the flyback converter, this is the formula which we are going to use for calculating the Lm. Okay, where delta Lm is my peak to peak ripple current. Okay, you know that basically what is my output current, and we can consider 20 to 40% of the ripple current. Okay, so that is up to the you how much stringent requirement you have to put while designing the things. Now we are going for the average and magnetizing current using the power balancing. Okay, so what is the average and current that should flow? Okay, so here I am assuming that the 100% efficiency is there, so I will write it down Pn equal to P out. Okay, so what is my Pin? Vs into Is, and what is my output? V0 into I0. Now if you see that, okay, so my output V0 into I0, I can write it down V0 square by R. Okay, and this is Vs into Is. Now what is my Is? So Is is my input current. You can see here, so Is is my input current. Okay, so this is the Is which is flowing. Okay, so this Is is there. Okay, and this my IL, this particular Is, and this is my ILM. So ILM is there. So when Is is equal to the, I can write it down that my input current is equal to the this particular magnetizing current only when in during the on time, that is the dt time. Okay, so d time only my ILM basically Is equal to ILM. Okay, that is I know, because when switch is on, that time only the Is will flow. Okay, but this ILM will be circulating here. So I can write it down Is equal to DILM, right? So the same thing I have write it down. I have just replaced the Is with the DILM, and this Vs is there, and output side V0 square by R is there. So from that particular thing I have derived the ILM expression. So I am getting the what should be the maximum, what it should be the current which can flow through the ILM. So average and value of the magnetizing current. Okay, so this is the expression we have derived. So if you do the simulation or not, the same kind of current you will get. Now what I am doing is that I am substituting the value of the Vs. Okay, so we have this expression V0 equal to N2 by N1 into D divided by 1 minus D into the Vs. Okay, we have already derived, and this is already known to you. Now I am substituting, I know what is the value of the Vs here. Okay, so I have just substituted the value of the Vs, which is this particular value, in this particular ILM expression. So now after substituting, so this is what I am getting, and if we rearrange the terms and all, so I am getting the one final expression of ILM. Okay, and this is the average and inductor or magnetizing current. Okay, so this is the value you should get. So I hope so till this particular point we have seen that. Okay, so this is the one formula how to derive the Lm value, okay, while designing the magnetizing inductance, and what is the average and value of the current which will flow. So this is also another important parameter which will be select while designing, while selecting the actual inductor. Okay, what is the average and current that is flowing through it. Okay, so this particular thing I hope so you understood. Now we will move forward and we will see the inductor current, that is magnetizing inductor current analysis at the boundary between the CCM and DCM. So you know that basically whatever we have talked, that is with respect to the continuous conduction operation. Okay, now we should have the knowledge of basically if it is goes in the DCM, what is the minimum value we should keep for LM. Okay, so that thing also we need to know. Now when we go for the DCM, what is the meaning of the DCM? This IL minimum might be go to 0. Okay, so that is the case when we can call something as a DCM. Now you can know that there are the two things which are there when we go. So what is the maximum value and minimum value? So you know that maximum value of this particular case can be ILM average in value plus delta ILM by 2. Okay, and this delta ILM already we have derived, and ILM we know that it is an average in value which we have just now derived. Okay, and if we go for calculating the minimum inductor current, okay, what is this IL minimum should come? So it is ILM minus delta ILM by 2. Okay, so this is the basic formula applicable for all the DC to DC converter. Now I want to go for calculating between the CCM and DCM boundary. Okay, so what will happen at the boundary condition is that this IL minimum is equal to the 0. This is what I have told you. So if I will keep this particular value to be equal to 0, so I will get ILM equal to delta ILM by 2. Now I have all the values available for what is the value of the ILM I have, what is the value of the delta ILM I have. So I have just substituting this particular value and I get one expression for the LM. So this LM expression I got, and this is the minimum value of the LM to ensure the CCM operation. So this particular value we have to keep, okay, when we design the value of the LM which we have derived the formula. Okay, so I will just check once with this particular value, and then after that I will see whether that value is less or what, in condition with the boundary condition. So I will check using this particular formula as well, okay, whether it is in the CCM or DCM. So this thing we have to ensure as well. Okay, so I hope so you understood that this is the how we have derived the boundary condition for flyback converter. Okay, so till this particular point everything is clear. Now how to derive the what is the formula for capacitor sizing? We have seen that there is a C0 capacitor in the flyback converter. So this is a well-known formula for the capacitor calculation, which is delta V0 by V0 is D upon RC FSW, where FSW is my switching frequency. So this is the formula. Okay, so if you want to go in detail, just apply the simple IC calculation based on when switch is on and switch is off, and current second balance you can apply, you can easily get this particular formula. Okay, so this is how we will derive the things, and you can use this particular formula of the C for calculating the output capacitance. There is one important note is there when a capacitor current note. Okay, what is that? The peak to peak capacitor current delta IC is approximately equal to the maximum diode current, which is equal to reflected magnetizing current in the secondary of the transformer. Okay, so peak to peak capacitor IC is equal to what? Maximum diode current. Okay, so this is the one note. Okay, if somebody asks you, so you can remember. Now what are the key waveforms associated with it? All these things we will see. So we have seen that what is the V1. Okay, basically this waveform is for my V1, or we can see that this waveform is for the VLM. Okay, so V1 and VLM both are same. So when switch is on, basically V1 is there. When switch is off, V out into N1 by N2 voltage is there, and if we do the average of this, it should be equal to 0. Okay, that is the volt second balance. Now what is the IS, input voltage? So input voltage is go from some minimum value to some maximum value IS, okay, during the on time, and when switch is off it is 0, right? And this is the secondary, how this will reflect on the secondary IS into N1 by N2. This is secondary current. Okay, or we can see the diode current. So when switch is off, that time only diode will conduct. So from some maximum value it will go to some minimum value, and output I'm always want my output to be a constant number. Okay, so whatever the desired output I should have, so those thing is there. Okay, so hope so till this particular point everything is clear to you, like how we are designing the flyback converter and all. Okay, now we will move forward for the design problem of the flyback converter. Okay, like now we will take this same problem and we will do in Matlab as well. Okay, open loop as well as closed loop simulation. Okay, so we are continuing with our design problem. So some parameters I have considered, like the input voltage is 24 volt, output voltage is 50 volt, and my output power requirement is 50 watt. Okay, and I'm assuming that the my output voltage ripple is 0.3 volt. I'm considering, and the switching frequency of my converter is 250 kilowatts. Okay, so these are some specification which I have considered for my flyback converter. Okay, now with this particular specification we can start. Okay, so what things we needed? So first thing first, like first step is to output voltage expression. So we know the well-known output voltage expression for our flyback converter, that is what? V naught equal to Vs into D upon 1 minus D into N2 by N1. Okay, now I am rearranging the term to find out the value of the D. So I have just rearranged the term and I got some expression for D. So that is D is something I got. Now second thing which you have to consider is a turns ratio assumption. Okay, so how much turns ratio you want? So some basic common sense. Okay, so my input voltage is 24 volt, output voltage is 50 volt, so I am boosting up. Okay, so definitely on the secondary side I need a higher turns ratio. Okay, so I am considered here as N2 by N1 is 4 is to 1. You can consider 8 is to 1, 10 is to 1. That is all up to the you. Okay, so how you are designing your inductance, that is all on in your hand. Okay, now just something I have considered turns ratio. Now with this turns ratio I have started calculating the value of the D. Okay, So just putting the values and calculating it, I got the D is equal to something 0.3425. So with this 0.3425 and with this turns ratio, I can achieve the desired output voltage for my given input voltage. Okay. So this is what I have. Okay. So if I consider some 8 by 1, N2 by 1, I may get D is something different. If I consider some different turns ratio, I got some different D. Okay. But for what D, for N2 by N I have considered, I got D is equal to 0.3425. So either I will do in open loop and closed loop, I need 34.25% as my duty. Okay. So this is for sure for this particular N2 by N1. Now second thing is a load resistance. So I have my P naught available with me 50 watt, and I know V naught is a 50. So my I naught should be 1 ampere. This current should flow, and resistance is V naught by I naught. So my load resistance for this particular case is 50 ohm I am considering. Okay. Now we have the value of the basically D available. Now I am going for the output capacitor sizing. So we have seen the derivation, or we have seen the formula, what is the value of the C which we can use, that is my C out. So that is D into I naught divided by FSW into delta V naught. So delta V naught, I have my stringent requirement of 0.3 volt. So I have just keep and calculate the value of the C naught. So generally I have considered some bit higher value. So I consider C equal to 5 microfarad. So this is the minimum required value I need to keep. Okay. So I can keep 10 microfarad, that is also fine. But in my simulation I have used the 5 microfarad. Whatever the value we have calculated, I have keep the same. Now C value is done. Now important is the LM calculation. Okay, because LM is very important in the flyback converter. Now for designing the LM, I should know what is my magnetizing current that is going to be flow and all. Okay, so we know the average value of the ILM that goes to flow. So we have derived this particular formula. So I just substituted the value and I got them 6.08 ampere of the current that should be going to flow through the ILM. And I'm assuming here is that basically some 40% ripple is there in my delta ILM. So based on that I calculate so 0.40 into 6.08. Okay, so 2.433. So this much of basically ripple I am allowing, okay, while designing the inductor. Now what is the minimum value and what is the maximum value of the inductor magnetizing inductor current that should be flow? So those things I have calculated. Okay, just for my reference, if I will see the simulation waveform, I should get nearly equal to these values, because whatever theoretically we learn, that should reflect practically as well. Okay, now magnetizing inductance value. So this formula we have derived, LM equal to D into Vs divided by delta ILM into FSW. Okay, I have just substituted the value and I got some value. So this is the required magnetizing inductance value we have calculated. So this parameter you have to keep while you substitute the value in the transformer. Okay, so I will tell you in simulation how to do that. Okay, so LM value we calculate. Now we, what I had told you, that we will check for the CCM boundary condition. Okay, whether that particular value which we select, that is 13.5, and whether it is greater than or less than the boundary condition. So for boundary condition, to ensure the CCM, we have derived this particular thing as well. Okay, I have just substituted the value and I got that 2.70. So 2.70 13.51 microhenry is greater than 2.70. So okay, whatever value I have selected, that should be work in the CCM. Okay, it will not go in a DCM operation. So since the LM equal to 13.551 microhenry is greater than 2.70 microhenry, the design satisfies the CCM condition. Now so here we have basically justified that, okay, whatever value of the LM I have selected, that is in the CCM mode only, because what is the minimum value requirement, that is we are more about that. Okay, now what is the source current? So I have already told that D times the ILM is my source current. So this is the source current which is going to be flow, that is 2.008 ampere. So we have all the data available with us. Okay, so from this particular document, what we have learned is that what is the fundamental operating principle of the flyback converter, then how to derive the different parameters, how to analyze the circuit in the CCM and DCM. Okay, so all the things we have learned. Now what we are going to do is that we will switch to our Matlab window, and there we will simulate the flyback converter. What are the different things we need to consider while simulating? All those things we are going to discuss. Okay, so just initially we will see this basically open loop simulation and what is the problem in the open loop we will see, and then we will go for the closed loop simulation. So here in this video I have just voltage mode control I am going to implement for you. I will not go into how to tune the parameters. That things we have already learned in our previous sections of this video, like how to tune the buck converter, boost converter. So the transfer function is only the required to tune, but I am not going to go through that part in this video, but you can need it. I will make one video on how to derive the small signal modeling of the flyback converter. Okay, so now we will shift to our Matlab window. So here we are in our Matlab window. So the same design problem which I have discussed, that same parameter I have taken. Okay, so my input voltage is 24 volt, output is 50 volt, and output power is 50. Okay, the same thing I have calculated. Okay, switching frequency is 250. N2 by N1 we have selected 4 is to 1. Okay, the same thing. Duty ratio, how to calculate, the same formula I have used. Delta V naught, how to calculate, and I have considered some stringent requirement of 0.3 volt. Then C naught calculation. Okay, output capacitance based on one, basically how to do that thing also I have deal. Then ILM, what is the average value of the maximum inductor, that ILM, maximum value of the magnetizing current and minimum current, those things also have calculated, average value. So all these things I have calculated here. Then LM calculation I have done, and I have checked for LM, okay, whether it is in the CCM or DCM, and what is my input current. So all these things I have calculated and I have just run for you. So you can see that the same D which is I have calculated there, the same thing I have got here. So this is just a script file I have written down. So every calculation I have done in my script file. Okay, everything related to whatever parameter we have calculated, like the C I got, D I got, okay, FSW is there, ILM I have calculated, ILM maximum, what value it should go, IL minimum. So these parameters also we have calculated in our that Word document as well. Okay, now LM I have calculated, LM check I have done. Okay, everything I have calculated here in my workspace. Okay, now I will just move to our Simulink model, and I will show you there the complete block diagram. Okay, now this is the simple flyback converter I have drawn in basically the Simulink model. Now what is there? So this is the my basically VS available. Okay, V in 24 volt. Now I have keep the switch here. Okay, so this switch is very important. Okay, so I told you that you should keep this at the bottom, not at the top. Okay, and this is a drain source, and I am going to get the gate. Okay, so this is the MOSFET I have considered. Now this particular is the my pulse generator block. You know how to take the pulse generator block, and inside this I just have to mention some parameter like amplitude is 1, switching frequency I have mentioned, and whatever duty we calculate. So I told you that 37.24 is the duty I required for my turns ratio of N2 by N1 is equal to 4 is to 1. Okay, so this thing I have done. Now important thing is basically how I connected. Okay, so you can see that this is the linear transformer. So if you just search a linear transformer, you will get a linear transformer. Okay, now what things we need to do while doing that. Okay, now I have linear transform, I have taken it, so its polarity is already defined. Okay, so it is plus, it is plus. So I told you that for our flyback converter, plus should be at the bottom side. So now this transformer is there. Okay, so what I have done is that basically this plus is at the bottom, which is connected to the ground, we have seen in our circuit. So I have just used this terminal to connect at the bottom part, and the other terminal, which is a non dot terminal, that I have connected to my diode. Okay, so this is the thing we need to do, right? So I am making the my dot convention as it is, which is there in the flyback converter. Okay, so you can see the videos also available there. They have keep this terminal here. Okay, but that is wrong thing. Okay, because we have to see the dot convention as well. Okay, while doing the thing, when you go in actual hardware design of the flyback converter, you have to make the connection in the same way. Okay, so that is why the same kind of thing I have done in the Matlab as well. So now my diode is there. So another thing is my capacitor, which is I have kept, and another is my load resistance, that is 50 ohm, which is we have already calculated. Now I have choose the linear transformer, but where is my LM? So LM, every parameter, where is my turns ratio, everything is inside this particular block. So I just open this particular block. So initially you do the SI unit. So my P out is I have keep at 50. Okay, so the same thing which I require, I can keep it as higher, that is not an issue. My switching frequency, because it is a high frequency transformer, so I have to keep the switching frequency as it is. Okay, so 250 kilohertz, that same thing I have mentioned in the script file I have given. Now what thing I need is that my turns ratio should be n2 by n1 should be 4:1. So I have just keep v in, okay, and I have keep the 40 into 10, 40 here and multiply by 10. If I divide this two n2 by n1, so I will this secondary parameter by first primary, I will get the 4 by 1 n2 by n1. So you can see that 40 is there and 10 is there. So I have just keep some higher voltage. You can keep directly, but keep in your mind that it should be input side should be greater than 40 volt and output side will be greater than 48 volt. Okay, so this thing you have to keep in your mind. So just I have make the turns ratio. I am assuming here is that the whatever the losses is there, that is R1 primary side resistance and secondary side resistance, primary side inductance, secondary side inductance. I am keeping this parameter as 0 as of now. So I am considering as more of an ideal transformer. Okay, and second is RMM. Okay, I told you that RM is there, so we generally keep it open circuit by keeping it infinite, but LM is a very important parameter which we should keep, okay, in our mind. So whatever LM we have calculated, I have just keep this value here. Okay, so this is my LM parameter. So hope so this parameter you know, and this is very important parameter for energy transfer. Okay, so don't ignore this parameter, otherwise your simulation will be wrong. So this is how we can keep the values. Okay, and once all the things are done, I have just run the simulation for you. So running the simulation, and you can see that what output I'm getting. It is taking a bit time. So my output requirement is a 50 volt, 48 50. Okay, but now you can see that its steady state value reached to 47.75, some average in value. Why? Because there is some losses here, and I though it is a ideal transformer and it is open loop case, so it will not reach to 50 volt. Maybe sometime it will reach or maybe sometime not. Okay, so that is why there is a requirement of closed loop operation. Okay, so I will just show you waveform once. Okay, so I am not getting 50 volt exactly. Okay, I reached nearby. Okay, if I will vary a duty a bit, I may get up to 50 volt. Okay, but that is not the case. uh, I'm not getting exact 50 volt. So we will do the closed loop simulation as well, but I will just show you the waveform first. So I just open my scopes so that you can see once. So the scope is open, so you can see that. Okay, so I go my output current requirement is a 1 amp. Okay, that thing we have seen. Okay, we calculate, and output voltage requirement is 50. So but I am not getting 50, but I got something around 47.9 to 47.6. Okay, so that is fine, but current is very important. Okay, because nature of the current will determine whether it is a basically oscillatory type of nature, whether it is CCM or DCM. So it is not going zero, so it is a perfectly CCM. Okay, we have ensured the CCM operation. But what kind of nature it has, because it should have. Okay, so this is the perfect nature which we required. Otherwise you have, I have told you in one of the class that basically sometime you got the output voltage, but the nature of the I naught or IL is something different. Okay, so that is a instability. Okay, if you implement that thing in hardware, that is not going to be work. So you have to make sure this should be the nature. Okay, so increasing, decreasing, this kind of nature is there. So this is I naught. So if we plot the IL, so same kind of nature also we are going to get. Okay, so this is how we will do. So I will just plot the IL for you so that I can show you. So this thing is already there, a scope, one scope is there. So I will just open the scope and I will show you. Okay, so you can see that. Okay, so 0 is achieving. So what does it mean? That operation. Okay, but this is the input current I'm showing you. This is not the LM current. Okay, so that is why it is going 0, because I don't have a provision right now. If I will keep the inductance outside, that time I can show you that. Okay, so it is maintaining the CCM, but this is the nature which we have seen. We have seen that 7 ampere should might be the current that is going to be flow, right? Average and current through the source is less, but what is the peak value we have seen? So the same peak value, whatever calculation we have done, the same kind of nature, same kind of value we will getting. Okay, so this is how we will basically do the open loop simulation. So I hope so you understood this thing. So this is very important thing. Okay, so open loop simulation is very important in this particular case. Now we have seen that output is not reaching 50 volts. So for that I need to go for closed loop. Okay, so just a very simple voltage mode control I will implement for my flyback converter, and we will see that. Okay, so now right now if I will do in closed loop, I am getting the desired output. Okay, so just move to the closed loop simulation. So here we are with the closed loop simulation. Okay, So again the same script file I have. Again input voltage 24 volt, output voltage 50 volt, and output power is 50 watt, and the switching frequency is 250 kilohertz. And the same parameter I have calculated, n1 by n2 I keep it again 4 by 1, d everything I have keep as it is. Okay, lm everything I have calculated. Okay, now with this parameter I just basically going to implement the closed loop control. Now here a simple voltage mode control I have considered. Okay, I am not tuned the parameter. Okay, I will show what is the problem if you are not going to tune the parameter and all. Okay, what kind of instability you will get, and why there is a requirement of the small signal modeling, and why there is the importance of how to tune the controller. Okay, so you will learn. So you can see that again the same flyback converter I have used. Okay, the same thing which we have seen. Okay, now what thing I have only changed here is that this PWM block. So this PWM is generated by this voltage mode controller. You know the basic operation of the voltage mode control is that we have the reference output voltage, which is my 50 volt, which is compared with the actual, and it is going to be passed through the one PI controller, and then this is just my PWM generator, and this will be compare, and just simple PWM will be generated. Okay, now here I am keeping some random parameters. Okay, so I have not tuned it. Okay, I will show you what problem it will come. So I have just keep some random parameter of P, KP, and KI. Okay, and with this parameter I'm getting the 50 volt as output. Okay, but what is the issue I will tell you. So I have keep some KP and KI parameter, and I have just run it. Okay, I will just run one time for you, and you can see the output as well. Okay, so the output you can see that initially it is 0, and then with the time changes this output is 48, 49, and I am going to get nearly exactly 50 volt as an output. Okay, so this is the simulation environment. So I have just implement the voltage mode control, and reference my actual, it will try to make it 50, and after very quick time you can see that my output I am getting as 50 volt. Okay, so I'm getting, okay, that is fine. So whether this is completely correct or not, no, I will say if you implement these values in the hardware, this is going to be not work. Why? Because I will show you the waveforms. So I will just stop the simulation, and now we will see the waveforms. So you can see the output voltage waveform and I note. Okay, so just a small I have done the simulation, so you can see that. Okay, so you will see, sir, okay, it is coming 1 volt 1 ampere, which is my required output current, and this is again I naught V naught is 50 volt. Oh, that is fine. But if you zoom this particular waveform, you can see that there is a instability is there. Okay, so this instability is there, and this is not the thing which we require when we do the hardware. And that is why I will say, even though your output is settled at 50, but still there is a instability, and because of this instability very high current will draw from the input side. Also the losses will be more, your system will be hit up more. Okay, and losses will be more. So that is why I always say you have to learn how to tune the controller. Okay, and those videos I have already covered in my one of the playlist for basically controller design for DC to DC converter. Okay, for buck converter, boost converter, how to implement the voltage mode control, how to implement the current mode control, all those things we have learned there, right? So I hope so you remember those videos as well. But anyway, I just wanted to show what is the problem. Okay, when you implement the closed loop control, so that is why the phase margin, gain, crossover frequency, these things are bandwidth, these things are very important while designing the closed loop control. Okay, so if possible, if I get the time, I will make a one video on small signal analysis, small signal modeling of the flyback converter, and then again we will do the one closed loop simulation there, where you can see that basically there will be no such instability will occur. We will get the output voltage as 50 volt, and on the same time instability will not be there, because we will tune the parameter of KP and K. Okay, so for this particular video, that's all. Oh, thanks for watching, and I hope so you enjoy something. If you enjoy something, if you learn something from me, please like and share the videos. Okay, thanks for watching.